In this lesson, we're going to project a multi-block mesh onto the surface of two intersecting pipes. We are going to combine two parts using the COSURF command, build a multi-block mesh with shell faces, delete unneeded faces from the mesh, rotate part of the mesh on an axis, explain the block command, find the coordinates of a node, add a plane and project to it, explain how projection cures surface discontinuity, show the anatomy of a block structure, and lastly, the anatomy of a tsave file. TrueGrid meshes are shaped by projecting faces of the mesh onto surfaces. This is known as the projection method. The projection method makes it possible for TrueGrid to faithfully conform the meshes to any geometry. The projection method is quick and easy. Step 1 is to create the geometry by defining the geometry using TrueGrid or by importing it from a CAD data file or a combination of both. Step 2 is to build the topology of a crude approximation of a mesh and then move it into position near the geometry. Step 3 is to project the mesh onto the desired surfaces. Notice that the edges of the mesh that are common to both pipes are automatically placed at the intersection.
We're going to import the geometry from a CAD system this time. We're only going to use the outer surfaces of these two intersecting pipes. I'll label the surfaces, and what I want is surfaces 7 and 5. So I'm going to tell it to only show surfaces 7 and 5. So I'll pick 6 and remove it, and 8 and remove it. So we have two intersecting surfaces. Now I'm going to get rid of all of these lines. We don't need those in the picture.
As you progress in using TrueGrid, you will use the menus and dialog boxes less and less as you memorize the commands. When you see a command you haven't learned yet, in one of our videos, pause the video and go to our online manual and search for that command, or use our in-program help to read more about a command. Find the command in the menus and activate the help tool to read the in-program help. The reason that TrueGrid was first developed was to solve the problem created when meshing two or more surfaces that didn't have perfect geometry at the unions. The projection method was the way that we solved this problem. The first thing that we're going to do here is combine these two pipes.
So when we build a composite surface, we typically use the COSURF command. We give it, let's say, surface number 10. So now this combined surface is called surface number 10. And when you click on 10, you see both of them highlighted.
Now we are going to build a multi-block mesh that we will project to the surface of this combined pipe, part number 10.
So I go to the parts menu, the block command. Now in the I direction, that's in this direction like this, because that's where X is, we're going to have a face here, and no face here. So I'm going to use a -1 to say that we have a face. The minus sign means there's going to be a face here. And then I'm going to have a -11 for here. There's going to be a face there. But in the third location in our topology, it will not be a minus sign because there is no face that covers this hole. So that'll go to 21. So it's a -1, -11, 21. Now in the J direction corresponding to the Y, we're going to have a face down here and a face up here. So there'll be two minus signs, a -1 and a -11. And in the K direction, that's from here to here to here. We're going to have a face or a minus sign here for K1, because we don't have something covering this hole, but we do have this face right here. So I'm going to have a -1. And then similarly, we have a face right here in the K direction. So I'll have a -11 again. And then 21, we'll put node 21 here, but it's not going to be negative because there's no face here covering that hole. So it's 21. Now for coordinates, I'll have x go from a -2 to a +2 to a 10. Now in the y direction, a -2 to a +2. And in the z direction, this is going to be our symmetry plane at 0. And then we'll put this at 4 and this at 10 in the k direction, or actually the z direction. So we have minus signs producing shell faces everywhere. And we can see it here as well. Let's put it in film mode, fast graphics. Shells everywhere. So in the I direction, we have a face, a shell structure, or face for this part of the cylinder. We have a shell structure right here to cover this part of the cylinder. And we don't have a shell filling in this space right here, which corresponds to minus, minus, plus. Now in the y direction, we have a shell structure at the bottom and one at the top, so that we have shell elements that'll cover this, this, and the opposite faces down here. And finally, in the K direction, we've got a shell structure here, not because we want to fill in this hole right here, but because we need this portion of it for this part of the face of the pipe. And similarly, we needed a second partition for this part of the face. Now you look at that and say, well, how is that going to work? They aren't even close to where they should be, which is correct. And I'll show you how we fix that. So first of all, I'm going to rotate it exactly 90 degrees. I need to throw away blocks that I don't need. Otherwise, it gets too cumbersome. I don't need that face. And I don't need the one down below it either. So I'll delete those two. Also, there's a face inside here that I don't need. And there's a face inside here that we don't need. Let's put it in hide mode to see. It's this one. That has to be deleted. So now we've got our pipe here. And we've got this pipe here that's not in the right location. Easily fixed. I'll rotate it exactly 90 degrees around the x-axis. Put it in wireframe. Select this face here and move it into position here so that it's close enough so that when it projects, we get the desired result. We go to Move Points, Rotate. I'm going to rotate this around this axis of rotation. Just rotate it around to here and let go. And now everything is in position. We have the block structure just as we need it. We can now project all of the faces onto surface 10.
In the computational window, we're going to use the nodes and bars to select all of the faces of the mesh all at once so that we only need to issue one projection command.
So I'm able to select all of the faces. And now I want to pick surface 10 and project. I'll get rid of the surfaces in the picture. I'll get rid of the highlighting and we'll turn on the hide. Now there's still a problem with this. It's not perfect. And fundamentally, the problem is there's too much curvature for the projection to do a proper job. So we have to help it along with a 3D curve. And that's this edge right here. You got poor quality elements, collapsed elements here. We need to create a 3D curve so that we can attach this edge to that curve and then have it project, and it'll be a beautiful mesh. Well, that's for surface number 7. So I'm going to display surface number 7. And I'm going to remove some of the mesh from the picture. But I'm going to take that out of the picture for the moment. It's a region to be removed. So now we're looking at part of the mesh as it sits on this surface.
Now we are going to attach this edge of the mesh to a 3D curve that follows this surface.
So I'll label the surface edges and take the union of that edge and that edge to form a 3D curve. You're beginning to see that 3D curves play an important role in building the meshes. So that'll be curve number 1, and it'll be edge of a surface. I've selected this here. I'll type F8 to enter it. And then I'll append to that the edge right here. F8. So now, instead of using edges of the surface, I now have a curve. And I can pick that labeled curve and attach. And that fixed the mesh. Now I'll put everything back in place. I'll remove the surface. I'll remove the curve, put it in hide mode, get rid of the highlighting.
You can see that we have a beautiful mesh at that interface now. Let's go back to the tsave file and look at the lines of the block command. One might ask, when do you use a minus sign and how does it work? Think of this as a solid mesh to start with. Then go back and change the signs to minus anywhere where you want a face to turn into a shell. For example, we could have started out with a solid block mesh using this same 1, 11, and 21, and so on. Then we go back and ask, do we want this to be a solid or a shell? If we want it to be a shell, we change it to a minus. The base integer remains the same. There are many examples to practice in the training guide, so you will get the hang of this.
We start out with a solid block structured mesh. This one has 4 blocks. And you'll notice in the block command, 2 blocks in the I direction, 1 block in the J, and 2 blocks in the K. So that gives us our 4 blocks. And the dark black lines represent the partitions in our block structured mesh. So you can see where each one of the 4 blocks are located. Now, if we wanted to turn this into a shell that formed a box, I is in this direction. So we want this face to be a shell. So we would go to the 3rd partition in the I direction and make it a minus. Now we would also want this hidden face back here to be a shell. That's the 1st I partition. So we would put a minus on this 1. Now in the J direction, the 1st partition in the J direction should be minus. So we would put a minus right here. And the last partition in the J direction would be a shell structure. So we want to put a minus sign on the 2nd partition. Now, if we want it to be a box, we want to make sure that we have a bottom to it. And that would be the hidden face down here. And that's in the K direction. K is orthogonal. The K direction is orthogonal to that face, so we call it a K face. It's the 1st partition in the K direction that would be minus. Remember I said a -1 and a -8 in the I direction? That's this face and this face that turned into shells. And in the J direction, both 1 and 3. 1 and 3. And in the K direction, just the 1st I want to point out to you some problems that are inherent in the way the geometry is set up. We can deal with it. Let me show you what I mean by that. I'm going to look at this node right here to get its coordinates. And you'll see the coordinates printed out right here. And notice that the z coordinate is a little bit above 0. That's not so bad. But there's another node over here that's not acceptable. It's 0.08 when it should be 0. Well, the cause of that is TrueGrid projected faithfully all of the nodes to their closest position along the surface from where they started. And for some odd reason, this node right here ended up with a z-coordinate of 0.08. Now, if you want something to be on a plane, you have to project it. Now, in this case, we need a surface that's a plane where z is equal to 0. So we will create that surface. Okay, surface number 11, and it'll be a plane through a point with a given normal. And we want the plane to go through the origin, and we want the normal to this plane to be 0, 0, 1. So then I'm going to project this set of nodes onto the plane. And now it may even appear to be better, but let's check it to be sure. So I'll remove all the surfaces. And then we'll look at the z-coordinate of different nodes along this connection. There, z is equal to 0 exactly. That was our worst node. So now this is capable of being reflected to form the K-pipe. But I thought I'd show you a little bit more about the projection method so you understand the full magnitude of its capability. For example, this edge right here, it was only projected to one surface, that is the composite surface of 5 and 7 that we call number 10. And we ended up with something that's slightly curved. Now, what if I'd like that to be straighter? I could create a plane and project this edge to that surface, to that plane. And that's exactly what I'm going to do. So I'll create, again, a surface, this time surface number 12, and it's going to be a plane passing through 3 points. And I'm going to use Cartesian coordinates for all 3 of them. And I want that plane to go through this point. So I hit F7 to print the coordinates of this node into this field right here. I want the plane to go through this point as well. Hit F7. And I want it to go through this point right here. And then I'm going to project this edge onto this surface. I also want this edge to be projected. So both edges are now going to be projected to this plane. I'll remove that surface now. And you'll see it cleaned up this edge beautifully. This edge was already projected to the composite surface. By projecting it to the plane, the algorithm, the projection algorithm, automatically found the intersection of the plane and this composite surface that we call 10. And it placed the nodes equally spaced along that intersection, that 3D curve intersection of those two surfaces. Except that this vertex, this corner node of this edge, it is also on the symmetry plane. So for that vertex or that node, it had to be placed at the intersection of 3 surfaces. That would be the composite surface, the plane that formed this, and then the plane that forms the symmetry plane. And the reason I point this out is because this is a profound feature in TrueGrid, that it automatically finds the intersections of surfaces. Now there's another characteristic of this surface, or this composite surface, that you should be aware of. The surfaces don't meet. They don't meet properly. I'll remove the mesh from the picture and I'll show the composite surface. So here's our two surfaces. Now, typically, when building a mesh, your mesh generator has to find that the surfaces meet perfectly. But in TrueGrid, they don't have to be meeting perfectly. You don't have to fix up the geometry if you're building a CAD model. TrueGrid compensates for these small errors, but this is a very significant capability. And I'd like to tell you a short story about airplane manufacturer where they were trying to pass a test by the FAA, and they lost cabin pressure because the door seal failed. Well, they had a door seal model in a CAD system that had around 100 surfaces, and some of them had gaps between them, and some of them overlapped, and some of them were tiny little slivers, and they were having to mesh each one separately and try to glue them together, and it was a horrendous problem. And we told them how to fix that problem by simply taking the composition of all 100 surfaces to treat it as one, and you project to the one even though there might be gaps between the surfaces or overlaps, and it worked beautifully. It took them just minutes after they had spent over 9 man-months trying to do it the hard way. So again, I want to emphasize just how significant the projection method is. So let's suppose this is surface number 7, and this is surface number 5, and there's a gap between them. It's a small gap. They always are small. They're not huge. If it's huge, you've got a real problem. But typically, it's a small gap. And you take the union of these two surfaces and you say, now project to the union of those surfaces. Well, what does the algorithm do? It projects it to this surface and it projects it to this surface and moves that vertex or that node to the point that is closest. It doesn't try to fix that gap at all. And a similar thing happens if you're saying, well, I want an edge of my mesh to be on the intersection of two surfaces, but the surfaces don't quite meet. The algorithm, by no special case, will extend the surfaces tangentially to find the intersection. Again, no special case is considered. It's the routine algorithm. It's great. It's a really elegant algorithm. And so even when you want to intersect two surfaces that don't quite intersect, TrueGrid does a wonderful job of it. So you don't have to fix up your geometry. Your tolerances, your errors, should be relatively small compared to your element size. In a block structure, we have corners to blocks, and they can be controlled in 3 different directions because there are 3 different faces that meet at that corner. We call the corners of the blocks vertices. And then we have edges that connect one vertex to another. And then we have faces which are formed by nodes surrounded by 4 edges. And I'm going to end a TrueGrid, and I'm going to open up a file called tsave that was automatically created. I'm opening it up with VI. Okay, so this is everything I did in that mesh. And actually, there's some stuff we can take out. We don't need this header. We don't need these lines right here. That's just a comment. And we can get rid of these 2 lines. Oops. We can get rid of these 2 lines. They're not needed anymore. Let's see. We can get rid of the merge. We don't need that. So now it's been reduced to this file. I'm going to write it out as kpipe.tg. It's got 15 lines. And now I'm going to run TrueGrid using that as an input file. And we are exactly where we were a minute ago.
That's beautiful.
Now, just to put it in perspective, on numerous occasions I have asked our TrueGrid users, our expert TrueGrid users, what is the single most important feature in TrueGrid? And unanimously, they all say that tsave file that you can use to rerun, and you can modify it easily. It would be different if that session file was huge and complicated, but it's not. So here we read in the geometry from an IGES file. We made a composite surface. We created the block part. We deleted faces we didn't need. We rotated one of the faces into position. We projected everything. We created a 3D curve, and we attached an edge of the mesh to that 3D curve. We created a symmetry plane and projected to that symmetry plane. We created another plane that was perpendicular to the symmetry plane and projected edges to that. You see how terse this is. And these are the key commands that we use all the time. You'll find out that there's just a handful of commands that you really need, and the rest are kind of easy to figure out, and you don't really need them that often. These are the key commands, not many of them. Well, there's a few more that you need to know, but not many, and you'll see that as we go through the course.